And thanks all the organizers for putting together this amazing conference and program, and for inviting me and giving me the opportunity here to tell you a little bit about my work. So what I'm going to talk today is a project that I did with one of my students about sort of time delays, which has been kind of one of my favorite sort of topics to come back to whenever I need sort of an interesting physics problem. And so I hope you will also enjoy this. So this will be a theory talk, but just to connect a little bit to physics. So what I have in mind is what I'm going to talk about is basically some light matter interfaces and sort of the quantum many-body physics thereof. But all of what I'm going to talk about applies to sort of various types of physical systems that you might have in mind, and that I'm sure we will hear much more about during this conference. So what I'm thinking about is some sort of quantum emitter. This might be an atom, a quantum dot, or whatever your favorite quantum emitter is, that is coupled to a sort of a 1D waveguide in a regime where maybe all of the photons that the emitter emits are emitted into guided modes. And this might be, I call them photons, but of course, this might be a nanophotonic waveguide, but it might also be some sort of structure that, guides acoustic waves. So, from a theoretical point of view, all of this will sort of be described in a unified framework. And what I'm interested in is kind of networks of these things, where you have nodes with one or a few emitters that are sort of hooked up and connected by these waveguides. And of course, this sort of is prototypical vision of the quantum internet, as Jeff formulated it a couple of years ago. And of course, this you can do a lot of interesting things here, including quantum communication protocols. What I'm interested in this talk is more about sort of the many-body physics of such systems. In particular, I'm interested in sort of many-body physics of these nodes that can interact via exchanging photons in these channels, or maybe I can ask a question: what kind of photonic states can be generated in such networks? Basically, what's just the physics that we can study here? And there are, the way I see it, basically two, regimes that, one can sort of conceptually distinguish here, and they're very different. So one is a regime where, this photon propagation time between these networks, these network nodes is kind of negligible compared to all timescales on which these nodes evolve. And so this is kind of what we are used to in quantum optics, where you basically can eliminate the photons, and then you can write down a master equation for the nodes, and you have the full sort of quantum optics machinery to solve this master equation. The other regime, which is what I'm going to be more interested in for this talk, is exactly the opposite. So when these nodes are very sort of separated, and these photons here, either they're slow or you really have large distances, but sort of, the distance is such that the time it requires a photon to, from traveling from one node to the other one is not negligible anymore. And this is sort of an essential sort of non-Markovian setup in that sense, and you might have sort of non-trivial feedback loops. And the point is you don't have a master equation that, describes something like the reduced dynamics of the nodes. And even though it's sort of a kind of a, almost a paradigmatic quantum optical setup, it's actually, surprising how limited the tools are that we have to describe such systems. And so my talk is really trying to address that. So that's this talk. Okay. And so what I always find very surprising is, you can illustrate a lot of sort of the, conceptual challenge that comes into play when you have these, time delays and these non-Markovian environments by sort of a very, very minimal model. It's actually a very beautiful model, which is just like, you have a single quantum emitter that is coupled to a 1D waveguide, and you introduce some sort of feedback, coherent quantum feedback, by basically terminating the waveguide on one end with a mirror. Okay, so half of the photons that the atom emits sort of go to the mirror and come back and interact with the atom again. And now, of course, there are, again, two regimes. If this mirror is kind of close, such that the round-trip time is basically negligible, then, you can, of course, write down a master equation for this emitter. All this mirror does, it sort of changes the vacuum a little bit for this atom. And, you can totally solve this problem. It's just standard optical Bloch equation, essentially. And, you can even ask a little bit more interesting questions. So what is the structure of the output field here, the photons that you can emit from such an emitter? And you will quickly find the answer. Well, these are matrix product states. So they're kind of entangled, interesting, but, you can classically represent them efficiently. There is nothing that you cannot do on a classical computer with the system. And the real reason for why this is kind of simple is because there is no memory, or no effective sort of memory. And already in this sort of simple setup, if you move this mirror far away, far in the sense that this round-trip time for these photons is now long compared to the time scale on which this emitter evolves. So essentially, you can fit many photons into this waveguide. Then you introduce some memory. And already sort of this simple problem, if you have just a simple two-level atom, if you want, is not really solved in general. In a sense, there are regimes, there's a series of methods that people have developed to address this sort of paradigmatic quantum optics problem. But there's a series of regimes where all of these methods eventually fail. And this in particular includes sort of, methods work for like if there are only a few photons in the waveguide, or if you have only sort of a finite time delay, or if you are only interested in sort of short time transient dynamics. So, in these special kind of cases, you have methods that work here, but in general, it's not, it's hard. And one of the reasons why, it might be hard is that if you look, for example, at the output field in such simple setups, you can immediately see that, what you find is that the entanglement structure of the output field changes significantly. Before, when there was sort of like no memory here, the output field had a one-dimensional entanglement structure like matrix product states have. But as soon as you introduce sort of essential memory here, the output entanglement structure becomes two-dimensional. And that's really where the complexity changes. And a few years ago, we wrote a paper to show that, well, this output field is so complex you can actually build a quantum computer with such a setup by just measuring each photon that comes at the output port one by one and do measurement-based quantum computing in this type of scheme. And actually, sort of Oscar Painter, sort of not so long ago, did an experiment with superconducting qubits, demonstrating the basic principles of that kind of proposal. So that kind of was for us a little bit sort of an explanation why this is actually hard. And but we asked ourselves, well, does it mean that we can really say nothing about sort of this regime, and or is there a way to deal with this problem nevertheless? And that's kind of what I want to do in this talk. Okay, so that's kind of my introduction. Let me now do a little bit theory thing and actually write down a Hamiltonian. So this is kind of my pictorial representation of my system and a sort of a waveguide that has sort of a feedback loop. Again, sort of think about the atom coupled to a semi-infinite waveguide. So I write down a Hamiltonian to describe this thing. And this contains a system Hamiltonian, which, for the entire talk, you might just think about a two-level atom here that is driven with a, Rabi frequency omega, and then, eventually can sort of radiate into this waveguide. And the waveguide is simply sort of free dispersionless photons, and there is a coupling in rotating wave approximation to this waveguide. And the reason why this is non-Markovian is, of course, because this coupling becomes frequency dependent when you make these time delays large. If the time delay is very short, then this frequency dependent you can ignore, dependence you can ignore, but when it's large, it becomes non-Markovian. So this is kind of the setup that I have in mind. And as I said before, if you make this time delay very short, what happens is, well, now you can actually eliminate the waveguide, and you see you can write down a master equation for the system that basically has some sort of coherent light shift from the interaction of the atom with its mirror image, instantaneous interaction, and some sort of renormalized radiative decays. So depending on where you put the atom with respect to the mirror, you can sort of suppress or enhance spontaneous emission into the waveguide. It's kind of all well known, and people have done beautiful experiments along these lines. In the other regime, as I said, there is no master equation that describes the system alone, because I just cannot trace over the radiation field. But what I'm going to tell you in this talk is I can sort of, equivalently, or I can think about this problem in an equivalent Markovian many-body problem. So the statement that I want to make is, well, this single body non-Markovian problem maps exactly into a many-body Markovian problem. And so a very special many-body Markovian problem that I will sort of introduce in a second, but that's kind of the main idea. And then, we have again a many-body Markovian problem, and we have a whole machinery that we can use to solve this, and sort of, or at least try to solve this, and we will see how that works. So, but let me just introduce this many-body Markovian model that sort of maps to this type of problems. So what this is, okay, I call this a 1D cascaded chain. So let me just try to, for those of you who are maybe not so familiar with sort of, in quantum optics, the cascaded master equation. So this will be the basic ingredient for this many-body problem that I'm going to study. So the problem is the following. Imagine I have two systems, system 1 and system 2. And they are coupled to a 1D waveguide, if you want, that only supports, photons propagating in one direction. So unidirectional channel, so the output of system 1 is fed into the input of system 2. And so, you neglect here time delays. Time delays actually don't matter if you have only unidirectional channels. So in that case here, you can write down a master equation that describes the evolution of system 1 and system 2, and this has been done, 30 years ago. So what you can do is sort of you just derive this master equation, and it's basically is a master equation that involves sort of local Lindblad terms for the evolution of system 1 and system 2, sort of independent ones, but then also this very particular sort of cascaded coupling that has this sort of strange commutator form. So, this has a unidirectional flow of information here, and you can, see this in this master equation in the following way. If you, for example, take the reduced state of system 1, sort of you trace over system 2, you see that system 1 satisfies a closed master equation, but the same is not true for system 2, right? Sort of the time evolution of the reduced density operator of system 2 is, contains system 1 sort of as a source. Okay, so that's a cascaded master equation for two systems. I mean, if you're uncomfortable by the fact that this doesn't look of Lindblad form, you can rewrite this and sort of write it in Lindblad form. It's a proper Lindblad master equation. But with this, I can now define sort of this 1D cascaded chain. And so the idea is very simple. I take, replicas of my system of interest, and I connect nearest neighbor via such a cascaded channel, okay? So you can immediately write down the master equation. The master equation is just a sum of sort of nearest neighbor Lindblad operators that are exactly this cascaded nearest neighbor cascaded master equation that I wrote before. Notice this is sort of different than sort of a situation that I think also many of you sort of studied in the past, where you take a single sort of chiral waveguide and couple many emitters to it. That would not only have nearest neighbor terms, that has sort of long range terms. This is really just the nearest neighbor cascaded master equation. Okay, so yeah, in a sense, this is in general sort of a driven, dissipative, and interacting many-body problem. Okay, so my statement before is that these two things are in some form equivalent, okay? And I'm going to now try to explain you exactly in which way they are equivalent and how one can see this. Okay, so for that, let me go back to my starting point. This was sort of my Hamiltonian. The first thing I want to do to sort of understand this mapping is I want to go from a sort of frequency representation of my radiation field into sort of a time representation. I introduce these quantum noise operators, the way all of you are familiar with, just as Fourier transforms of this of my bosonic annihilation and creation operators. And if I do that, I can rewrite my Hamiltonian that describes both the system and the radiation field again in the following form. So it contains the system Hamiltonian, which describes the dynamics of this alone, but then also terms where I have a jump operator, and it creates a photon at time t and at time t plus tau, where tau is the round trip time, and the corresponding sort of adjoint process. So the way to think about this is, well, I now have my radiation field that I sort of I have a mode, different modes that are now labeled by time. So these are boson. At each sort of point on this line, there lives a bosonic mode, and my system at time t interacts exactly with two of these modes: the mode that I label by t and the mode that I label by t plus tau. Okay, so this is how I think about this Hamiltonian and the sort of Schrödinger equation associated with it. Let me just now sort of give you a little bit more intuition about that. If you're not familiar with that formalism, let me integrate this Schrödinger equation, okay? And let me integrate it by introducing some sort of infinitesimal time steps and do some sort of stroboscopic integration. So if I have my wave function at the time t, the wave function that describes both my sort of system, but also all the modes of the radiation field that are initially all in the vacuum state. And I propagate this under this Hamiltonian for an infinitesimal time to the time t plus dt. So what happens in this infinitesimal time? Well, this will be a three-body process that involves the system, the mode at time t, and the mode at time t plus tau, according to the Hamiltonian that I had on my previous slide. So there will be a unitary that brings you from here to here, that takes as an input the state of the system, the state of the mode of time t, and the state of the mode at time t plus tau, and sort of spits out the state of these three subsystems after this infinitesimal interaction. And because my waveguide is initially in the vacuum state, it will turn out that it makes a lot of sense to always, assume that this mode is in the vacuum, and I just sort of absorb this lag here in this definition. Okay, so with that, I can now sort of, pictorially integrate this master equation. So I start out with my initial state of the system. This mode is in the vacuum state. The other mode is also in the vacuum state, and I sort of, apply the unitary to this input state. And then at the next time step, I need my system interacts with this mode and with this mode. Okay, so the state at time t plus 2 delta t, I apply another unitary that now acts on sort of the state of the system and two fresh modes that are both in the vacuum state. And sort of if time progresses, my system interacts with fresh modes all the time that are all in the vacuum state, and it builds up a sort of a quantum state on this delay, on this radiation field. And just as time goes on, this goes on until sort of a time t plus tau, when the system interacts with a mode that it already interacted with in the past. Okay, this is sort of when the photons come back. And so this is basically the state of this mode after the interaction. So what I will have to do now in the next time step, I will have to basically, write down a unitary that takes as an input the output state of this, unitary, the input state of the system at that point, and here at this side I have a vacuum input. So, if I continue with this whole process, you will see that I build up basically a 2D tensor network of the radiation field. So these are the labels of the states of the radiation field. And this is exactly what you find is this is a 2D isometric tensor network. And basically every state that you get out from just an atom coupled to such a delay line will give you a 2D isometric tensor network, depending on how you drive the atom, how you couple it to the waveguide. The state is a little bit different, but it's isometric. And as I said in the beginning, you can sort of drive this atom in such a way that this state is, for example, the 2D cluster state. And then, this state will come out at the open output port. Okay, so I promised you I wanted to bring you to the point where this kind of maps to, interacting many-body systems. So how does this go? Well, let me now not look at the state of the waveguide, but what I actually want to do is I just want to look at the state of the atom, the reduced state of this emitter. And so what I have here is the full state of, emitter. So this is the open leg that corresponds to the state of the emitter, and all the modes of the radiation field. So what I need to do is I need to trace over these radiation field modes to get the reduced state of the atom. So I take chi, the thing that I just constructed, bra and cat, and I trace over the radiation field, meaning I have to take two of these 2D tensor networks and contract all the legs that corresponds to, bosonic modes. The only ones that stay open are the ones here, which are sort of the system degrees of freedom. So this is, representation of the reduced state of the emitter at time capital T when I trace out all the radiation field. It's just, contraction of a 2D tensor network. The point that I want to make here is if I look at the transfer operator of this 2D tensor network, this transfer operator turns out to be the infinitesimal time propagator of this master equation. Okay, this is a little bit magic here, and I cannot really prove it, but that's kind of how it works. You can see sort of, why this can be true, okay? So if you look at this transfer operator, this, takes as an input, here, like states on the Hilbert space of the system. So for each leg here, I have, a replicated Hilbert space of the system, which sort of, basically, each input leg here corresponds to a replica of my system in my cascaded chain. And in that sense, you can convince yourself that this transfer operator is exactly at least acting on the right, Hilbert space. Okay, so once you have that, so you see this, transfer operator is the infinitesimal time propagator. So if you actually, take several, multiply these different layers of this transfer operator, you get a finite time propagator of your cascaded chain. So it turns out this entire network is just, a contraction of two, finite time propagators of this cascaded chain that's sort of depending on, at which time you look, one is sort of deeper than the other one. But that's kind of how it works. And the main idea here now is to, well, if you want to solve this, we better, we better construct this finite time propagator of this cascaded chain, which is a, Markovian, thing. And I can do that. This is the nearest neighbor interaction. I can use my standard, matrix product techniques to actually construct this propagator by doing, for example, time evolving block decimation algorithm. My zero time propagator is just is the identity operator, which is a product operator, which is obviously representable as a matrix product operator. And then I can just evolve it by doing time, evolving block decimation and try to construct my finite time propagator. And once I have the finite time propagator in a matrix product form, I can just, do this construction. So that's the key idea. Of course, the key question is, so I can also do this in sort of the, infinite system size limit, which corresponds to calculating the steady state, but that's a side remark. The key question is really, well, if I want to calculate the finite time propagator of such a 1D interacting many-body system, is how does the entanglement or the operator entanglement entropy of this propagator grow with kind of evolution time, which here is kind of time delay. If this finite time propagator becomes very highly correlated, then I cannot, then this TBD algorithm will fail, and the method just doesn't work. So that's kind of actually the key question. Like, if I want to solve this, is this finite time propagator efficiently representable as a matrix product operator? So that's what we are asking ourselves. And you can just do this, right? You can just, try to construct it and see what the entanglement structure of this, propagator looks like. And it turns out if you do this, for example, on this sort of paradigmatic toy model of this driven two-level system, indeed, just a numerical observation for all, regions in this parameter space, this propagator satisfies an area law. And in that sense, you can efficiently represent it on a classical computer. Okay, area law means just if I look at this propagator and I sort of make a cut, no matter where I cut, sort of the operator entanglement entropy is independent of the size of this thing. And it's also independent of, well, it doesn't grow with the propagation time. So that's nice. So what it means is that, we can actually calculate the atomic state and all sort of low order correlation functions, but also sort of slightly more complicated quantities like relaxation times and stuff like that, all efficiently using just these, matrix product operator techniques. And this really works here for arbitrary time delays. So tau can be very large. It works for arbitrary driving strengths. It works for arbitrary number of photons in the delay line. And it works for arbitrary sort of propagation time. You can go to the steady state. You can actually directly target the steady state with this method by just going to infinite sort of chains. And in that sense, you can really solve this problem in a regime that you could not solve before, just like there was no method that does it. Okay, so, we just did it, and like I can show you pretty pictures on what you get if you solve this driven two-level system. You can solve everything for transient dynamics, steady state populations, relaxation times, output spectra, output correlation function, just by contracting these type of tensor networks. I don't want to go into the sort of details of the physics. There are a couple of cute features that we can talk about, but the method is sort of more general. Of course, I talked here about this very simple example of a single atom in front of a mirror, but there are sort of much more sort of, you can take two atoms that are distant and interacting via waveguide, or you can start sort of cook up simple sort of networks with multiple atoms and waveguides, and you can do the same kind of procedure that I just did. And in the end, it turns out all of these things map to some form of, cascaded chains. And if the cascade, even for this thing, all you have to do is kind of calculate the propagator of a 1D cascaded chain and then contract it in sort of the fancy way. And that's it. So all of this works, and it works as efficiently as sort of the simple toy example that we just discussed. One thing that might be sort of interesting is if you look at this plot that I had before where I looked at the operator entanglement entropy of my propagator, which is sort of a proxy on, how expensive it is to, solve this problem with this method. You will actually notice that in this regime where you have very large time delays and very strong driving, it's actually very, very cheap. So it's kind of counterintuitive because this was sort of the hardest regime with many other methods, okay? And so what it means is, so the operator entanglement entropy here is actually very small. So this actually suggests that, maybe you can do some sort of, mean field ansatz for this propagator of the 1D cascaded chain because, well, the propagator is basically a product propagator, so, mean field should be good. And you can do this. You can do mean field theory of this 1D cascaded chain and sort of derive the corresponding equations of motion and actually see that, this mean field theory works actually pretty well in this kind of presumably hard regime. And it's kind of funny. From this method, you actually figure out that this regime where all of these other methods fail is actually not hard at all. It's sort of the simplest one where you can do a simple mean field theory. Okay, so just to conclude, let me just tell you sort of where do things go wrong, okay? It's like not something that solves everything. Where do things go wrong? Well, first of all, you might wonder, how does this actually, go together with what I said in the very beginning, where I said you can do universal quantum computation with such a system. How can it be that I can calculate now everything, okay? Well, I cannot calculate everything. I can only calculate very specific things like the, reduced state of the emitter or low order correlation functions of the environment. If you would want to do measurement-based quantum computation by doing measurements on the output field, what you would need to do is you need to measure sort of all photons in the output field because that's what measurement-based quantum computation is, which basically means you have to calculate very, very high order correlation functions of the output field. And you can sort of convince yourself that in this tensor network formalism, it turns out that the computational cost of calculating high order correlation functions grows exponentially with the order of the correlation function. So there is no conflict, but it's sort of cute how it sort of shows up in this method. What else? Well, if you have very different sort of multiple time delays in a network that are vastly different, this can lead to challenge because it, either you can see it as a problem which maps to cascaded chains with very long range, interactions, or actually to higher dimensional problems. So eventually, sort of this, our method to solve it really relies on the fact that this 1D cascaded chain is really one-dimensional. If you have, this type of situations, then this will no longer be the case, and you will have problems. And also, the examples that we looked at, sort of this, single atom in front of a mirror, what happened is the corresponding cascaded chain is basically rapidly mixing. So you go to a steady state pretty fast, and that's fundamentally why the matrix product operator has an area law. If you change how, what your, atom is, the structure of the atom, how you drive it, you might run into situations where, you map to a 1D cascaded chain that is not rapidly mixing, and therefore, the method might fail as well. But actually, I mean, that's, I think, actually the most interesting regime, and we're actually thinking about how to get there, because this would allow you to generate sort of interesting photonic states in the output field that are maybe sort of more entangled than just sort of a fixed point state of like a 2D cluster state. Okay, with that, I think I'm out of time. Let me just sort of, basically remind you, I hope I convinced you that this physics of this, even few body networks with time delays is super interesting, because on one hand, it connects to sort of, Markovian-driven dissipative many-body physics. It also connects to these tensor networks and quantum information language. So I think it shows how much actually interesting physics is hidden in very, very sort of simple quantum optics problems. And with that, I just want to highlight Xenia, who is a PhD student in my group, who actually did all of this work. And thank you for your attention.
Yes, many questions. Kanu?
Thanks for the nice talk. So, in this picture of where we draw correspondence between an emitter in front of mirror delay and the cascaded chain, how do the physical parameters?
Oh, okay. Sorry. Yeah, I was maybe. Okay, here you have some sort of system, right, that has some physical parameters. What happens here is basically each of these systems in the cascaded chain is a replica of this system. There's a local Hamiltonian. In addition to this cascaded interaction, there's a local Hamiltonian, which is the Hamiltonian, the system Hamiltonian of that system during sort of, this here has the system Hamiltonian of the system during the first round trip time. Here, you act with the system Hamiltonian of the system during the second round trip time, and so on. So all the physics or the parameters that determine the system are sort of encoded in this chain in that way.
Is it right that the separation between adjacent emitters is the delay time?
Well, in this interpretation, yes. So each of these replicas you should understand. I actually wrote it here and I didn't say it. Each of these replicas should be understood as sort of a replica of this system at different round trip times. And in a sense, it's sort of not really hard to understand intuitively this mapping, in the sense that, well, you have the emitter, it emits some photons towards sort of a delay line, and after round trip time, this emitter basically is driven by, the output of its past. And this is basically this guy. It's driven by the output of sort of a copy itself in the past. And so on. Yeah, that's kind of how you should think about this.
So I have a follow-up question to that, if I can.
Yeah, quick.
Okay, great. So we studied this problem for two emitters with delay. And in that case, if you look at the reduced dynamics of the two emitter case, it does end up being a time convolution that's raster equation with a time dependent effectively.
So what you're saying is you started a problem with 2 emitters coupled to a joint waveguide. The emitters are distant, and then you map it to a Markovian 2-emitter problem with a time-dependent gamma that might, does it change with sign? Or is it always positive?
It changes with that.
Oh, okay.
So,
I'm not super familiar with that particular work, so maybe we should.
Okay, yeah, maybe then, many questions. Ana Maria, Giovanna also said, and Anna or Ash, yeah, many people.
So my question is, in a real system, for example, it's magic to have a system that is very highly entangled for the point. So what are the requirements? I mean, there is an extra dissipation perhaps within our free space. So what are the requirements that you need to have something that operates like a highly entangled?
Okay. Yeah, this kind of, I guess the question, we asked ourselves the question, back in the days when we thought about generating cluster states with this thing, is of course super important question if you really care about the output field. And I mean, in the end, the requirements are that while your emitting system needs to have a coherence time that sort of allows it to, generate entangled photons. So typically your emitter has to have sort of an internal memory that has to have a longer coherence time than the, how many photons you want to entangle. The other thing is, of course, that's very important is sort of the cooperativity. If you have a cooperativity of 10, you can get maybe to a 10 photon cluster state, but eventually then you will lose a photon, and depending on which state you generate, that might be a problem or not. You can think, we also wrote a paper about maybe you want to generate not just 2-dimensional cluster states, but sort of 3 cluster states where you can sort of tolerate photon loss and things like that. But I think the answer then really depends very much on which specific state you want to generate.
Giovanna.
So thank you, Hannes. That was very interesting and very elegant. I have a question regarding the definition of the temporal modes, because this is sometimes tricky, and also in connection to how much can you stretch the value of tau towards small values, because gamma tau, I understand, is a limitation to the description you apply.
So I'm not entirely sure I got the question. What is the actual question about the definition of the temporal modes? Sorry.
Because you need the distinguishability based on
yes.
time, so they have to be orthogonal in a sense.
Yes. So of course, I mean, when you write down this Hamiltonian quantum optics, typically you have sort of, this is only true over some bandwidth, and this bandwidth then introduces a cutoff, and all of this is sort of swept here under the rug. But it's kind of the same oh, now I see your question. So your question is if the time delay is actually so short that the feedback mode and the thing overlap, yeah, then this breaks down. Yeah.
But can you quantify it in a way to say, because this will also give a condition on the form of the wave packet that you form. They have to be like Gaussian wave packet. If they have tails, you would have a problem with the distinguishability. Like overlap, you need a commutator between B or T and B. So T plus tau dagger to be 0, say.
Yes, I mean, we didn't really think about it. I mean, we were obviously interested in the opposite limit, but yeah, we should talk about that. Yeah.
Then Anna, Ash, and if we have time, Rahul. But Anna.
Thank you very much. So there is something I'm missing. So when you were talking about multiple emitters, I know we have discussed that even in regular waveguide theory, which is bidirectional, things become hard just when you scale up. But somehow you said, well, you can scale up the number of emitters, and this is still efficient. Is it because there is some chirality?
Oh, I think that's. Thank you for the question. Obviously, that's kind of what is sort of a priori not clear, right? We basically map this to this 1D cascaded chain, and a priori it's not clear that this has an efficient solution in terms of matrix product operators. And so now you ask me, is there a good reason why, how I can explain sort of this numerical observation that it actually is. And I think the reason is that the interaction is basically sort of, dissipative if you want. I mean, if you want, okay, do I have a picture? Okay, this is kind of stupid. But, so if you want, in order for this thing to interact with this one, it kind of has to send a photon down this channel. It might be absorbed by this one, or it might just be lost here. If it's absorbed, then this can sort of send it down this channel. It has again a chance to get out. So in order to establish very long-range correlations, the kind of interactions are kind of exponentially damped, if you want, or the effective transmission of correlations sort of is exponentially damped with distance, in a sense. That's my intuitive understanding. Whereas if you have sort of just as things you consider like a 1D waveguide with multiple emitters, then you have like just pure long-range interactions, and that makes it much harder.
Yeah, Ash.
Thanks for a great talk, Hannes. I guess there are a bunch of things I could ask. I'll stick to one question. So there's another community that's interested in these cascaded chain models. So basically, non-reciprocal models can have weird homological properties. There's this funny localization that comes up in a non-Hermitian skin effect. It seems like those effects could show up here, or you could actually use this kind of setup to study those models.
Absolutely.
But do you see this kind of localization that has launched a million papers in the field of non-Hermitian physics?
We have not seen it. We have also not looked at it very carefully. So this is as kind of a pet project that I do with one of my students. So we didn't have a lot of time to sort of study these things. But it's exactly sort of a great question. I think one of the things that I like about this is kind of shows you that you can actually study with simple experiments if you want many body sort of driven dissipative models. And I could imagine that, it would be super interesting to sort of study what do you have to do to your system to, and effectively engineer a many-body model that has interesting properties. I think that's exactly one of the, yeah.
Rahul, you wanted to ask? Oh.
So thank you for the very nice talk. So I had maybe a question, so maybe two questions which are related. So the first one is that if you allow your emitter to be driven, can you form any iso-TNS in the photonic field, or is there something?
That's a very good question. So it depends very much on what kind of sort of, the short answer is it depends on what kind of interaction you have between your emitter and your waveguide, and what kind of control you have over your emitter Hamiltonian. If you can generate the proper interaction, the proper Hamiltonian, every iso-TNS is for free, I think so. But I mean, in practice, is one of the things that we are studying right now is, of course, in practice, you have sort of certain interactions that an emitter and a waveguide can have, and certain ways you can drive it. And then there are interesting questions: which type of iso-TNS can you actually realize? Yeah.
So in that case, then in the last slide, when you mentioned that your reconciliation of this with the METC was that METC based on high order correlation. But then an iso-TNS, even local observables should be difficult to compute. So in some, if it is completely generic, there would be certain iso-TNS that are injective that are even.
Yes, that's kind of what I had on my very last slide. Sorry, like I think there might be. So I agree that there are some states where even sort of few body observables are hard in an iso-TNS. And that would correspond to driving the system in a very specific way with the corresponding interactions to the waveguide. So I think one of the really interesting questions is really how can we generate those states? That's sort of one of my sort of outlook. I should have emphasized it more.
Yeah, maybe there was one last quick, Helmut.
Could you also apply this to the case of a loop, and then, or would this be a three-dimensional? If you have in this ring cavity type of thing, there would be alternative methods to solve it and test it.
I'm not sure what you mean by just a ring cavity. Well, in principle, a very long ring cavity. Well, then it's like a very high, like it's just a multi-mode cavity if you want, but really with multi-mode. like many modes. If the time delay is very long, you just have many modes. And
would this be then a 3D type of cluster state? Or?
I think it depends on how you couple the field out. If you have a it might be that you have that you can interact then with a photonic mode sort of several times in a sense effectively, and then you can have higher dimension, like more than just this, simple 2D. That might be the case. Yeah.
Okay, so thanks for all the questions. Has been a very interesting discussion, actually. So let's thank Hannes again.